Hello again, statistics students. Our topic for this session is general random variables. As you know, we've been talking about probability theory, the mathematics of uncertainty, and points A through G dealt with basic probability concepts and probability rules. And our discussion and our examples in all cases there was situations where we had qualitative data. Did they buy the product? Did they see the ads? Things like that. Now in random variables, we turn our focus to quantitative data. A random variable is an uncertain quantity. A quantity, a number that we can do arithmetic with. Random variables are exceedingly important in business. Most of our scorekeeping in business is done with numbers. Accountants keep track of revenue, cost, profits, market share. Almost everything we do in business is to meet or fulfill anticipated demand. Most often that demand is unknown in the future. Unknown quantity, it's a random variable. When we make decisions and pick different investments, investments yield a profit. Profit's a number. When we pick between investments, we're picking which random variable we're going to bet on. So as always, we start each topic with an example. Let's look at the example of playing roulette. So let's suppose we take a hard-earned dollar and we plunk it down on red. And I want to know, what's my profit going to be from that $1 bet on red? So if we put down $1 and a red comes up, they give us $2 back, our original dollar, and $1 profit. If we put $1 down on roulette and a black or a green comes up, they take the dollar away. So the profit is, if it's positive, it's a gain of $1, and if we lose, then we have a loss of $1. Profit can be plus or minus. Sometimes we have gains, sometimes we have losses. If we defined our random variable to be, say, return from a $1 bet, we either get back nothing or 2. But if we call it profit, we get back either +1 or -1. So as you can see, we have quantitative data. When you give me the probabilities for each of those, then you've given me a probability distribution. The probability distribution gives me the sample space. Here's everything that can happen, and then it shows me the probability of occurrence. So that's our first probability distribution. Every random variable has a probability distribution. Only random variables have probability distributions. The next thing we do after developing the probability distribution for a random variable is we find this E of X, and that's referred to as the expected value of X. So in here, capital E means find the expected value of, and whatever is in the parenthesis is the particular random variable of interest. This is sometimes referred to as the Greek letter mu. We use the symbol mu for the expected value. To find the expected value, we add up each thing that can happen. In other words, the first column times its probability, the second column. So you'll go row by row, probability times value, probability times value, probability times value to find the expected value. And what does that represent? That is the long run average. What in the long run? What's going to be the average profit per play of betting red on roulette? If we take the -1 times the 20/38 and the +1 times 18/38, we get this expression. Turns out to be -238, 2/38 or -0.053. This is exceedingly important by the law of large numbers. The law of large numbers guarantees that if you do a number of repetitions of, if you play roulette and bet on red over and over many times, it is high, with a very high probability, that your average loss per play will be around 5.3 cents per play as the average. And we can further make probability statements, exact probability statements about this, as we will be able to do in the second half of the course. By the law of large numbers, we guarantee that with 95% certainty that you're going to lose somewhere between 3.3 cents and 7.3 cents per play, or $330 to losing $730 if you play and bet on roulette 10,000 times. To illustrate that, I've created this simulation. So we spin, it indicates, we get a random number, it tells us whether it's a red or not a red, it gives me the economic consequence, and what we're interested in is this cumulative column here. This is the cumulative or running, the total profit, and then we divide that by the number of trials to get our average profit per play. And if we go down to the bottom here, after 10,000 times, we lost 6.48 cents per play, or $648. Is that in the bounds of what I expected? Yeah, I expected us to lose somewhere between $330 and $730. And pictorially, here is the law of large numbers. It says the more repetitions you do, your running average pretty soon is going to flatline. And where's it going to flatline? Pretty close to 5.3 cents. If you say, oh, I think you put the fix in on that, let me draw another random 10,000 random numbers and do another simulation of 10,000 plays of roulette. And it's pretty close to the 0.053 that we expected. We lost $564, or 5.4 cents per play. And do it one more time just to illustrate it. 0.054 again. And one more time, 0.057. So no matter how the story starts in the beginning here, the punchline is always that we're going to flatline eventually by the law of large numbers, and that number is going to hover around the expected value. That is the law of large numbers. Here's another bet we can make on roulette. We can bet on a specific number. If we bet on a specific number, if we happen to hit that number, they give us back $36, of which one was our original bet. So we're up 35. If we don't hit the number we picked, a specific number, then we lose $1. So here's our second random variable. The sample space is numbers or quantities. Give me the probabilities, and I have a probability distribution. One way out of 38, the number 23 come up? And there's 37 out of 38 ways that whatever number we pick, say 23, doesn't come up. We take probability times value, and lo and behold, it's the exact same value. There are no good bets or bad bets at roulette. They all have the exact same payoffs. So you cannot be a good roulette player. First off, you can't be a good anything where it has independence and it is a game of chance and not skill. But in this case, there are no particular good bets or bad bets at roulette. Unlike craps, where there's a couple really good bets and a couple not so good bets that have different expected values, the expected value of every bet you get in roulette is exactly the same, and it's 5.3 cents to the house. So, but this one has much more, let's say, riskiness, much more variability. Another great word is much more dispersion that takes place, and our interval that we're going to predict, I'm 95% sure that we're going to fall somewhere between making 6 cents average per play and losing losing 16 cents per play, or we'll make somewhere between $600 and losing $1,663. Demonstrate this one. We have another simulation here. Notice that we don't flatline near as soon as we did with the first bet. That is because this random variable has much more variability than the first one. And this will be measured by something called the variance. So if we have something with has a much higher variability, we're going to need more repetitions before the flatlining takes place. After 10,000 repetitions, we've lost 7 cents, well within the bounds of what we were predicting. Do a couple more random selections of 10,000, losing 8 cents per play. That's well within our bounds. And again, losing 8.5 cents, well within our bounds. So there's much more variability. We need many more repetitions. Oh, here's one where we actually ended up winning $224 after playing 10,000 plays. But again, that was within the bounds of what I predicted we looked at the example. So X has a smaller variance than Y. I don't know how to calculate it, but there's something called the variance, which measures the variability, the amount of difficulty we have in predicting the value that a random variable will take on. So let's step back and see what we learned. Let's look at the theory associated with general random variables. Random variable is an uncertain quantity. They come in two types. Discrete ones, like the one we just looked at, the sample space for the one we just looked at for red was -1 and 1. And there were gaps between these values. There's a whole number of numbers between -1 and 1. Our sample space consisted of, a listing, or if we were going to put it in a row, it'd be a bunch of commas. 1, a comma, -1 was the values. And the discrete random variables have gaps between them. Continuous things that we're uncertain about, like a person's height or weight, or how many tons of coal a coal mine will produce this month. We just take the coal out, dump it, and weigh it, and it can be anything, and we can weigh it to 1,000.23678 tons, and we're just limited by our machines. But the weight of something is actually a continuous random variable. We saw that random variables have probability distributions. Only random variables have probability distributions. We list the values that can happen and show the probability or likelihood of occurrence. Okay, if it's a discrete probability distribution, it's sometimes called a probability mass function. And if it's a continuous probability distribution, it's sometimes called a probability density function. We have something called the cumulative distribution, and it's the probability of being less than or equal to some value. Stay tuned for that. We looked at the expected value, and for our discrete case, we saw that it's probability times value plus probability times value plus probability times value. If it's continuous, we need the worm, we need the integral sign, and we find it using integral calculus. Obviously, we will not be doing any of those directly in class, but here is your statement, your notes. Here is a complete statement of everything. This is how, in reality, it's done, even though we don't need integral calculus in this class. The variance, to find the variance of x, sometimes known by the lowercase s Greek, sigma squared, uppercase sigma, lowercase sigma. So the variance, sometimes known as sigma squared. To find it for a discrete random variable, we take each value that can happen, say how far are you away from the expected value, square it to get rid of the sign, and weight it by its probability of occurrence. If it's continuous, obviously we get the worm out, but the only reason I put this here is so you can leave this out on the kitchen table when you're done studying, so your parents see it and they think we're doing something really high tech in business statistics, so they'll write another tuition check for you. The variance has an alter ego called the standard deviation. And obviously, if one's sigma squared and one's sigma, they're related because one's the square root of the other. The standard deviation is the square root of the variance. If the standard deviation is 5, the variance is 25. If the variance is 25, the standard deviation is 5. Why do they have two measures of the same thing? Don't know. Rule 7, I have no clue what that is. And Rule 8 says the law of large numbers. Over any large number of repetitions, the running average will approach the expected value. As we saw last time, I gave you illustrations. There is no such thing as the law of averages. It's a layperson's term who really have no comprehension of statistics and probability theory. The only thing we have is the law of large numbers, and the law of large numbers only talks about the future. It says nothing about the past. Let's look at an example. Problem 1 on page 8. Buster Gutt works at a local sporting goods store and sells, obviously, weight sets, given that name. Letting X represent the number of weight sets sold in a given day. We look at our records for the last 100 days, and we see that we sold either 0, 1, 2, or 3 weight sets. Here's our frequencies. So like we did before, we look at frequencies, and from them we generate probabilities. 20 over 200 is 0.1, 40 over 200 is 0.2, 60 over 200, 0.3, and 80 over 200, 0.4. X, our uncertainty, is a quantity, and now you've given me the probabilities. You've stated the probability distribution. Part A asks you to find the cumulative distribution, the probability being less than or equal to some value. What's the probability we are less than or equal to 0? Well, that only happens if we're equal to 0, and that's 0.1. What's the probability we're less than or equal to 1? If a 1 or a 2 pop up, we're less than or equal to a 1. 0.2 plus 0.1 is 0.3. What's the probability of being 2 or less? Well, if a 2 or a 1 or a 0 pops up, we're 2 or less. 0.3 plus 0.2 plus 0.1 is 0.6. And finally, all cumulatives end in 1. By the time we get to the last value in the sample space, to that last value of our random variable, the probability of being less than or equal to that is 1. If you ask me to forecast tomorrow and what demand will be tomorrow, our convention is we pick whichever one has the highest probability. If I was going to give you 10 bucks, if you could guess right what demand would be tomorrow, you'd guess 3 because it has the highest probability. The expected value, 0 times 0.1, 1 times 0.2, 2 times 0.3, 3 times 0.4, add them all up. On the exam, all you'll do is write that, and then I will give you a check figure. What a great guy. What an all-around swell professor you ended up with. Because I will do the calculations and most of the problems for you and give you a check figure. You just write the expression. If I say write the expression for the variance, and I've given you the check figure for the expected value, you go 0 minus 2, and then square it times 0.1, and then 1 minus 2, square that times 0.2, 2 minus 2, square it times 0.3, and 3 minus 2, square that and weight it by the 0.4. And on the exam, this will be a sufficient answer. That will be the final answer. Don't go any further. And it turns out to be 1. What does that mean? At this point, can't say a lot. Is that big or small? It's always relative to what? We'll put more meaning on the variance later. If you ask me to forecast the total number of weight sets sold over the next 30 days, on each individual day, I'd guess 3. But if you ask me to guess the sum of 30 days, I'm going to say, okay, expected value, come on down. Now I'm going to use, you give me multiple days demand, and I'm going to invoke the law of large numbers and say, we got 30 days, and they're going to average 2 per day. I think we're going to have demand of 60 over the 30-day period. So when we have multiple days and we want to forecast those, then we will take the expected value of our random variable and multiply the number of days we're forecasting. Part E says Buster earns 60 bucks per day plus $40 commission for each weight set. Ooh, I think I know the part-time job I'm going to apply for now. What's the expected daily salary? So I have a new random variable called salary. I don't know what my salary will be tomorrow. It is dependent upon my already defined random variable of demand, X. So it's 60 is my salary. If I don't sell any sets, it's 60 plus 40. If I sell one set, if I sell 2 sets, it's 140 bucks. And if I happen to get lucky and sell 3 sets, then I make 180 bucks. So I take 0.1 times 60, 0.2 times 100, 0.3 times 140, 0.4 times 180, and multiply those together, and you get $140. That's the long way of doing it. There is a shortcut. If we look here at our values for salary, and we say, well, each one of these we added 40 bucks, right? To go from here to here, I added 40, from here to here, I added another 40, from here to here, I added another 40. So what happened is I started with my original random variable. I gave you 60 bucks, and then I multiplied each X times 40. That is referred to as a linear transformation, and that's what Rule 7 is talking about. It says if you form a new random variable by adding a constant or multiplying a constant times the original random variable, you don't need to go back and do all of the multiplying and adding. You have a quick shortcut. You can simply take A is 60 and B is 40 here. You can simply take 60 plus 40 times whatever our expected value of X was. It was 2, so you can simply do 60 times 2 times 40 and get 140. Okay, next let's look at something you won't find in any book, and that is Waddell's Guide to Analytical Thinking. I've been challenged with the task of teaching you, improving your thinking skills here in business statistics. And it is through this procedure that I'm outlining here that we will do this. This works for every class you have. This is a generic tool for analytical thinking. Number 1, become an efficient, focused sloth. Be deliberate. Sloths get a bad rap. They're slow and stupid, and they didn't fare well in the evolutionary food chain. Well, I have great respect for sloths because I like their deliberateness. They waste no energy. They do nothing without a purpose. When I had my software business, we would we'd have these large scale systems we were working on, and we'd have a series of deliverables we'd have to bring to the customer at specific dates. And if we're approaching our deadlines, I'd noticed that the employees were starting to thrash. anxiety level would go up, and people would worry about the upcoming deadline. And you've all seen people thrash. When you thrash, oh, what can I do? What should I do next? What should I do next? We have too much to do, and we just sit there thrashing, spinning our wheels, and accomplishing nothing. Okay? And what I would always do is I say the following: let's get it done faster. Let's slow down. Slow down, find something you can do, specific, do it, and move on to the next small thing and do it. And then do the next thing and do it. Don't worry about the deadline. Worry about individual small steps that are involved in getting us to the deadline. No wasted motion. Do nothing without a purpose. Do absolutely nothing unless you have a purpose for doing it. A couple of other good quotes from great Americans besides this guy here. John Wooden: never mistake activity for achievement. Okay, you have people who give you a lot of motion but no production. And John Wooden's basketball teams always were fast break teams, but he always said, be quick, but don't hurry. Don't rush. Be very slick and efficient, but don't rush. By this being efficient and sloth-like, it means don't multi-process. Single process. Focus on one thing, do it well, move on to the next. Next, and very, very important, is to visualize, to see something. We are blessed with this gift of being able to visualize stuff. You can visualize it in your mind's eye, or you can take a piece of paper and physically draw an image of the problem you have. I visualize all my decision problems, and I take out a piece of paper and I put everything that I know about it on the piece of paper, and I can see it. This makes things absurdly simple when you do that. Okay? Good quote. Don't move until you see it. Don't move until you see it. Don't move until you see it. He's got it. Ben Kingsley in Searching for Bobby Fischer. A really good, feel-good movie. It's about this young kid, this chess savant, who just has a natural gift for the game. And Ben Kingsley has been hired to be his tutor, to serve as his chess guru to help him, achieve his potential. And in the movie, your homework for next time is put in that quote and watch the clip. It doesn't come out well over Zoom, so I'm not. The audio is just not good enough to play. So earlier, he's teaching Josh, is the kid's name. He poses chess problems and shows them on the chessboard for Josh, and Josh just doesn't see what the next move should be given a given situation on the chessboard. And Ben says, "Here, let me help you." And he knocks all the pieces off the chessboard. And he says, "Now solve it." Meaning Josh has to visualize it in his mind's eye, not on the board. So this is what we mean about visualization. See it, okay? Maybe in your mind's eye, maybe in a picture. And so he's in the movie, he's playing the kid in the championship round, and the kid has made a mistake. His opponent has made a mistake, and Josh is looking at it, and Ben says to him, even though the kid can't hear him, Josh can't hear Ben, but he's saying, "Don't move until you see it, don't move until you see it." He's got it. He sees Ben's eyes affix on one of the pieces, and he says he's got it, and he goes on to win the match. Again, a terrific feel-good movie. A couple other quotes while we're here from the movie Moneyball, a good movie to illustrate how to apply business analytics. In this case, it was applied to the 2001 Oakland A's baseball team. They had 25% of the budget of the New York Yankees and put together a group of misfits who ended up setting the record for most consecutive wins. And after that season, virtually every pro football team adapted adopted business analytics as part of their procedures. Um, and so their quotes were, every at bat is like a hand of blackjack. We're going to become card counters at the blackjack table and turn the odds on the casino. Next is role play. I'm not talking about what you do on the weekends for fun. I'm talking about you as a consultant must be able to see and to become the decision maker for whoever you're consulting for. Unless you can see the world through someone else's eyes, you cannot consult for them because your attitude toward risk is different than theirs. When we role play, we say, I become the decision maker. I watch money come in and out of my wallet or purse, and then everything becomes very clear. Make it personal. You become the decision maker. Pretend it's your money. You'll figure it out real quick. We employ the law of parsimony, also known as Occam razor, named after William of Occam. Around 10,050, he got in trouble with the Catholic Church because he said a lot of things that what Aristotle claimed were wrong. And the church was a big backer of Aristotle at that point. And he said, because some of the stuff some of the stuff that Aristotle claimed, there were much simpler explanations for. And that's what the law of parsimony is all about. It is about creating aesthetically beautiful, simple solutions to very difficult problems. It is these very simple solutions. The law of parsimony says out of all of the explanations, that is almost certainly correct. The one that is the simplest is most likely the correct one. We don't solve big, ugly problems. We analyze them. We break them down into smaller pieces. And then we solve some of the smaller pieces, and then we synthesize the bigger solution. So we take giant problems and we break them down. We analyze them till we get them down to pieces that we can solve. We solve the pieces and then put them back. The trick is to using the systems approach so that our solutions that we have for the small pieces fit into the overall big solution. So we don't solve big problems, we break them down, we solve the smaller pieces and synthesize the bigger solution by putting those small pieces back together. Let us illustrate the visualization and maybe role play in this problem here. Problem 4 on page 9. The Double Indemnity Insurance Company offers an insurance policy to New York visitors. It covers you for 1 week and covers you against financial losses suffered by being mugged. 10% of the people in New York are mugged within a week, so 90% aren't. The visitor is mugged by a professional. We get whipped on for $2,000 losses. So they bring some kind of lube and get our rings off our fingers, and they know where they find all of our stashed money and so on, and $2,000. If an amateur mugs us, they only get our wallet maybe, and maybe an earring or two. $500. 60% of the muggings in New York are performed by professionals. There's a $50 deductible clause, and we pay $200 premium for the 1 week policy. So here we go. What do I want to know? Well, the problem says, what is the expected profit? I know immediately that my notation will be X equal profit. We want to find expected value of something. Only random variables have expected values. If I ever see the word expected in here, and whatever word follows that is the random variable of interest. I want to know what is the expected profit to the insurance company from this policy. So X is the profit to Double Indemnity. and what things could happen. I could get mugged by a professional, mugged by an amateur, or not mugged. And now we got to figure out what's the profit X to the insurance company and what's the probability. Well, let's start with the chance. What's the probability we get mugged? It's 0.90. And what profit would accrue to the insurance company? We're the insurance company right here, and we're watching the money come in and out of the insurance company. Here's our decision maker, insurance company right here. And if this happens, if you're not mugged, the insuree sent a check to us, so we make $200. We make $200 profit. If we are mugged by a professional, what happened? Well, here's my insuree. They beat the crap out of him and took $2,000. So $2,000 went from the insuree to the mugger here. And then the insuree made the claim with the insurance company, and then we sent the insuree a check for $2,000 minus $50 deductible. Minus $50 deductible. So here's our perspective. We want expected value to the insurance company. Okay. So what are the ins and what are the outs? $200 came in, $19.50 went out. Our net is we lose $17.50. $19.50 out, $200 in. If we get whipped on by an amateur, very humiliating. What happened? Wrote a check for $200 to the insurance company, got whipped on for $500, and we sent them $500 to cover the losses, less the $50 deductible. So 200 in, 450 out, we lose 250. It says 60% of the muggings are performed by a professional. Our first intuition would be to put a 0.6 and a 0.40 there. But then when I add up the probabilities, they add to 1.9. That cannot be. What this says is there's a 10% chance you're going to get mugged by when in New York on any given week. Then within that 10%, 60% of those are performed by professionals. So it is 60% of the 10% or 6% chance we are mugged and it's by a professional, and there's a 4% chance we're mugged and it's by an amateur. Do we add up to 1 now? Yes, we do. So now, probability times value, probability times value, probability times value, and we get that we're going to make an expected profit of $65 per policy. And this is exactly how we determine the expected profits from any insurance policy that you have. It's all done through the basis of expected value. The two biggest industries that make every decision based upon expected value, we've done examples of both today. They're the gaming industry and the insurance industry. Insurance people hire these nerds called actuaries. They don't want to associate with them, so they put them in a back room and lock the door and, shove a pizza under the door every day. And they give them the job of doing these actuarial analyses to see what kind of expected values we're going to receive from various insurance policies. All right, our practice problems are 3 and 5 and 9 in this section. And also we're at the point now to look at our life insurance problem, which is due in a few weeks. Let's take a look at that. So we're going to find the expected value to a insurance company of a life insurance policy on you, a 5-year term life insurance policy on you. It has a $100,000 benefit. We are going to assume that your age is not your current age, but your age is LM, where LM are the last 2 digits of your student ID. If the last 2 digits of your student ID are greater than 79, then you got to subtract 20 from it because that's getting too old to get life insurance. Doesn't make economic sense. So based upon your last 2 digits of your student ID will give you the age that you're going to do your expected value for. And then we go over to this site. You actually don't need that. All you need to do is to go to your browser and click Life Tables, and then find the one for SSA, the Social Security Administration, and we get something here. The early work and probability theory, the people who really put the statistics on the map, developed these things called life tables that we'll talk about when we get the second half of the course. So it gives you, if you're male, what's the probability you're going to croak with this year and your life expectancy, and if you're female, same thing. Let's see, most of you are 23, 24, 25, say. If you're male, what's your chance of croaking this year? 0.0016. If you're female, what the? It is less than half. What the? This is unfair. This is patently unfair. Women have a much smaller death rate than men. Well, what happens when we get to be, say, 40? Okay, probability of a male dying at age 40, 0.0024. Female, what the? This is grossly unfair. Oh yeah, women have that childbirth thing. It's fair. It's not as bad as it was. It's not double a rate. It's not quite double a rate, but it's almost double a rate. And as we get older, the rates get a little closer, but this is why most of your old age homes have females vastly outnumbering the number of males. So I did the example for somebody who's 56, and so I grabbed these values here. I need these probabilities for death. I'm a male, so I grabbed these. Females I would have grabbed over here. And what you're going to do is construct an Excel spreadsheet. Column A is you're going to put your age. Column B, the probability of dying. Probability C, the probability you don't die. And probability E, our profit. And F, the probability of each profit. And then in G, you're going to go probability times value, probability times value, probability times value, and take it out. I gave you instructions for each column here. And then I give you an example of it here. So at age 56, your probability, if you're male, of dying is 0.008477. So the probability you won't die this year is 0.991523. And if we look back at our example for 56, the premium is $2,000 per year. And let's assume that the premium, whatever premium you start with, it's going to stay that for 5 years. So even though at 56, 57, 58, 59, 60, it's whatever premium you start with that you keep for the whole 5-year period. So don't jump it to 3,000 at 60, just leave it at 2,000. So if I croak in year 1, the insurance company would have taken in 2,000 and paid out 100,000. They lose 98. You croak in year 2, they took in 2 years of 2,000 and pay out the 100,000. 58, 3 years of premiums were recorded minus the 100,000. 59, 4 times 2, $8,000 premiums, they lose 92, and then if you croak in when you're 60 in the 5th year, the insurance company loses 90,000. And then the last value is if you don't croak at all during the 5-year period, and the policy expires, and the insurance company keeps 10,000 bucks. To create the profit probability of profit here, I've illustrated it and how to, what command to use for each one of your cells. Cell B2, so to get cell F2 here, you just equate it to B2. To do F3, you say it's C2 times B3, and so on. I've given you the instructions. So what's the probability that you die during the first year? Well, that's this probability here. What's the probability that you reached year 2 and then died in year 2? It means you didn't die in year 1, so it's this, times then the probability you died in year 2, that. You died in year 3. You didn't die in year 1, times you didn't die in year 2, times you did die in year 3. You died in year 4. You didn't die in year 1, you didn't die in year 2, you didn't die in year 3, but you died in year 4, and so on. And then you made the 10,000, you didn't die in any of these years. So these 5 things multiplied together. Do they add to 1? Yes, they do. Terrific. We have a solid probability distribution here of values and probabilities. Probabilities all add to 1. Probability times value, 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 boom. Add them up. Insurance company is going to make almost $5,000 on this policy. That is the expected profit to the insurance company. This is exactly the way insurance companies price their policies. This is the exact work that actuaries do using these life tables. All right, so I will be glad to look at your solution ahead of time. Bring me a hard copy, and I'll tell you whether it's right or not. And then so you should get the full credit on this exercise, and I believe it's worth 4% of your final grade. Very good. Thank you. See you next session.